All right, section 10.2, today we're going to be taking a look at plane curves, so that's two-dimensional, right, curves in 2 dimensions, and parametric equations, and we are going to look at how to use our calculator to graph with parametric equations. It's going to feel a little bit like some of the stuff we did in polar, and a little bit different too, but there's some components of that in it. So to start with, we often find it convenient to describe a location in terms of the parameter time. Consider a batter hitting a ball. The location depends on the length of time after it's been hit. Therefore, we could talk about its two-dimensional location, i.e. where it is on the field. We could even talk about its three-dimensional location, where it is in space on the field, right? It doesn't say that, but we could do that. But it's all depending upon the time after which it's been hit, right? Braden, baseball, right? No. Who's baseball? Somebody's baseball. Is it you? Both of you are in baseball. So this makes sense, right? The baseball being hit is a function of time, but there is a location in space where the baseball resides at any given point. But it makes more sense to talk about that in terms of time, and that's where parametric equations are coming from, is this idea of describing the x, y, and potentially z locations in terms of time, all right? So this is plane curves, so we're doing in 2 dimensions, so this one's going to be in terms of the xy coordinate plane in this section, and then I think in 10.3 is when we see the 3-dimensional one. If not, we'll come to it eventually. All right, so that is x of t, y is y of t, and these are our parametric equations. So we're going to do an example. We're going to sketch the curve defined by the given parametric equation, and we're going to write the corresponding rectangular equation by eliminating the parameter. And as a portion of this, we'll look at how the calculator does this as well. Okay, so we'll get all 3 of those components in there. So the first thing I'd like for us to do is we're going to create what we would have done back in algebra course or whatever, like an xy axis, not axis, but like a table that has x values and y values, but we're going to have t values and x values and y values because our parameter is t. So we're going to have 3 columns. We're going to have t, we're going to have x, and we're going to have y. The t values you choose kind of depend on what the x and y equations are. These are in terms of trig. So since they're in terms of trig, we really want to find values that are nice to find for our trig functions to work with. So in particular, I'm going to do things in terms of our unit circle. All right, so I'm going to do 0. We're going to start time at 0. And then we're going to do the pi over 2, pi, 3 pi over 2, and 2 pi. You could be more detailed. You could do pi over 4s or pi over 3s or pi over 6s involved. That'd be fine. But I think this is going to give us enough of an idea of what it looks like to be able to gain what we're supposed to be gaining here. Okay. So if our calculator were doing it, this wouldn't be enough, by the way, and we'll describe why. So let's actually take a look at what happens when we plug in 0 into these equations. So if I put 0 into 1 plus 2 cosine t, it will become 1 plus 2 cosine of 0. What's the cosine of 0? 1. So if I simplify that, what am I going to get? 3. So this first one is 3. Whoops. Try again. We're going to do the same thing for y. So we're going to put it into negative 2 plus 2 sine of 0. Now, in particular, if you want to do this more quickly, just put these in as y1 and y2 in your calculator. We can do this fast, right? And before we change them into parametric, we'll do that in just a second. You can see how that works. But if you take your calculator and you put into y1, we'll make it happen quick. 1 plus 2 cosine of t, or cosine of x is what we'll type in. And then in y2, we're going to put the y equation, which is negative 2 plus 2 sine of t, or sine of x.
Y1 or y of t?
One of them in y1 and one of them in y2. Okay. So my x is in y1 and my y is in y2. And you can actually go into your table. So you can do second graph. That's your table function. If yours does not allow you to input values, let me know right now and we'll get that changed. Does everybody's allow them to put numbers in to the table? Okay, so we're going to put in 0. We're going to put in pi over 2. We're going to put in pi. We had 3 pi over 2.
I can't put it in mine. I just noticed.
Okay. And then 2 pi. Oops. Did anybody else have problems with being able to plug it in? So the table's right here.
Oh, table set.
Table set. The first one's let's get a list of values. Let's just go down the X column first since we have it. And if your calculator's doing what mine is, it's giving you values that aren't quite exactly what you're expecting. For example, the first one says 3, but the second one says 2.99992. Actually, is my mode right? My mode's in degrees. That's what happens when you're teaching trig too. Let's try that again. Okay, never mind. They're all beautiful values now. So I have 3, and then I have 1, -1, 1, and 3. Does that match all's? Wonderful. Let's do the y2, it's in y2. It's our y values. So I have -2, 0, 2, -2, sorry, and then -4 and -2. Does that look right? Okay, so here's what we're going to do. We're going to take an xy coordinate plane, and we're going to graph this. And we're not graphing t, we're graphing x and y. Okay, so here's x, just y, just like normal. And we're going to graph the ordered pair 3, -2. Right, that's where we're going to start. So 3, -2. And then we're going to graph the ordered pair 1, 0. And then -1, -2. And then 1, -4. And then lo and behold, we're back at 3, -2, which makes sense, right? Because we're dealing with trig functions whose period is 2 pi. So when we put in 0 and we put in 2 pi, we get back where we were to begin with. What image are you going to get if you connect these? Can you tell? Close. Okay, it's actually a circle. My circle's not drawn well. Let me shift it. There we go. So ellipse was really close. This one actually is an ellipse that's perfectly symmetric, so it's really a circle. If you try to connect these dot to dot, it does look like a square. Preston's not wrong on that. We do want to remember that there are values in between that we've sort of skipped over that give us that circular nature instead of it being a boxy sort of nature of our curve. The last thing that we need to be able to graph, and I'll do it in a different color just so it stands out, just make sure yours is big enough, like drawn, that you can see it, is that we need to show the direction in which we graphed this. So parametric equations have direction because they're depending upon time and how time is moving. So as time moved, this one had a direction that was actually counterclockwise. And there even are some questions that will ask you what direction is the curve going in. And you would be able to say counterclockwise or clockwise based on your graph. Are you ready to look at another mode in your calculator, though? Let's do it. Okay, so if you hit the mode button, you can go down. We saw function is the one we're normally in. PAR, parametric, is our next one. Then polar was the one that we did before. So we want to change this into parametric. Okay, if you hit y equals now, your y equals now has x and y in it. Do you see that? Not only that, but when you hit the button that says x, it's now going to enter t. Right? It entered theta when we did in terms of a polar. All right, so we're going to enter 1 plus 2 cosine t, and it really will say t when we hit the x button. And then we're going to enter -2 plus 2 sine of t.
This is fancy.
Great, is that cool? All right, let's just graph it and see what happens, and then we're going to go back and manipulate with the table or with the window in a moment. So just graph wherever it is and see what happens. Okay, so mine looks terrible. I get this one little squiggly piece. Okay? Check with the neighbors. See if yours matches theirs. There's a reason mine's doing that. I know why it does. It's not surprising, but... Okay? Some of you have graphs that look like ovals. Does anybody's graph actually look like a circle? Okay, so we have some that are looking like circles. Okay, so it depends on a lot of things as to what your graph is doing. I know why mine's looking like this. Mine's doing this because my t values are starting and ending too briefly. Right? My input t's are not giving me enough width. I need to go all the way around my circle, and mine don't do that right now for whatever reason, probably from some time I graphed something a year ago. Okay, so we're going to hit window, and you can see a little bit more what's going on. So your t min and your t max right there, and then the t step matter. Okay? The x min, x max, y min, y max, that's just like what you've seen before. We need the graph to be big enough, length and width, and that's all fine. Okay? If it's looking like an oval and we're talking about knowing that it should look like a circle, that's just because your screen is wider than it is tall. Okay? So there's a squaring problem going on there. That's fine. But the T-min, T-max is the more important issue here. So we know that this graph should go all the way around in 2 pi. And we should know that because we've got trig functions that have sine and cosine in them, and their period's 2 pi. So we need this to go from 0 to 2 pi on our Tmax. Okay, at least 2 pi. If you overestimate, what your calculator will do is it'll graph it and you'll still see it spinning, but it will be tracing on top of itself and you won't be able to see any new information going on. So we'll experiment with that in just a minute. But for now, 0 to 2 pi is what we really want. Your t-step, I would like for your t-step to say pi over 2 first, because that's what we did our table at. Okay? So we're playing with this just a moment so you can see what kind of a problem this creates. So your Tmin is 0, Tmax is 2 pi, and then your t-step is pi over 2, and go ahead and graph. What shape did you get, Preston? Oh, you've got an error. You didn't get a shape at all. Okay, well, let's check it out.
Okay.
You've got a line of size from that. Make sure you this when you start graphing. It's okay. Go ahead and hit. I think you're using Windows Pro right now.
Yes.
So hit just hit graph.
I have a diamond.
It looks like a diamond, again, because our window is skewed. It's actually a square, which is what you predicted it would be when we were trying to just connect the dots kind of perspective before. So what's happening is our calculator is only evaluating at the 4 values that we did, and then they're doing like the children's kids menus, you know, at the restaurants do it, and they're connecting the dots with straight edges. All right? We should look at this and say, that doesn't quite make sense. So what happened, and the reason it happened, is because when we did our window, our t-step, pi over 2, wasn't a very good t-step. Let's do one more play thing with it. Let's do pi over 4 and see if it improves. It will. It's still not going to be great, but if you hit pi over 4, look what happens. It looks like a hexagon or an octagon or something like that, right? It's actually an octagon. If you were to count it, it's getting you 8 points. It's starting to look more circular. Agreed? All right, let's make your window, have your t-step be something small. 0.1 is probably a pretty safe bet most of the time. It doesn't need to be dependent upon, pi over something values. If you do it at 0.1, the graph looks pretty smooth. And if you don't think that that's smooth enough, you can make it smaller than 0.1, make it 0.01. But I will tell you, the smaller you make your t-step, the longer it takes the graph to go. So you don't want to overcompensate here because you're going to just be staring at the calculator and being like, when is it going to stop? Okay, so let's manipulate our window one more time. Let's leave your t-step at 0.1. Let's make your tmax 4 pi because I'd like for you to see what happens when it does this. But here's where I want you to watch. When you hit graph, I want you to watch the graph in the top right-hand corner where it has sort of like the scrolling bar. And I want you to see how those engage with one another. So if you graph this, it completes the circle. It really is a circle. I know it looks like an oval. But the spinning thing is still going in the top corner, right? And the reason that's happening is because what it did is it went around your curve, and then it went around it a second time. But there was nothing really new for it to plot. Now, you might have looked and said, well, it looked like it made little places a little bit thicker. Well, it did. It's because your t-step was 0.1. So all those values the second time around were slightly different than they were the first time around, right? They were a little bit off. And so it filled it in a little bit better, but it didn't actually give you any new information. So your best bet is to really look at the graph and decide how far does my t-step need, or how far does my t-values need to go to get the whole picture. It only needs to go 2 pi here. So we don't really want it to go too far, and we don't really want our t-step to be too small or too big. 0.1 is usually a pretty good estimate. Okay, everybody good so far? Excellent. Oh, I should also mention if you go into your table here, you can do the same thing that we did before in your table. In fact, all the values got moved over. At least mine are showing up there. I assume that's why they got moved over. Do yours all have those t values that you put in for x on the other screen? Okay. So you don't have to be in a normal XY function screen to do what we did before. If you're actually in your parametric screen, it'll do it for you anyway. Okay, all good?
Is there any way to set the screen so it looks more circular?
Yeah, if you hit Zoom number 5, Zoom square, it'll square up your window and it'll actually look like a circle. Thank you for asking.
Thank you.
Okay, did everybody's look like a circle now?
Yes, it's
Ah,
a lot
wonderful.
nicer now.
Yeah, you definitely want to manipulate your window first with the Tmin, Tmax, and T-step before you start squaring it, but squaring can do that for you. Yeah.
You may not know from my calculator, but is there a way to set the table to do trig values? So it goes from 1%. Because my graph is
You'll have to research it. There probably is, because we have a table set in these, and Cassie usually has all the same functions. I just don't know how to do it.
Gotcha.
Okay. Everybody good with quick example number 1? Okay. There's one other thing that it said. It said by eliminating the parameter. We haven't done that yet. So the eliminating the parameter business here is not an easy thing to do with this equation. So generally speaking, what that means is I would like to solve for t in one equation and plug it into the other equation, thus eliminating t. Does that make sense? It's substitution. You've done substitution before when you've solved equations in like an algebra course. That's not really very friendly here. And the reason it's not very friendly is because the t is the angle and it's embedded inside of the sine and the cosine. So that's what this is describing. So to change it into a rectangular equation, into parametric form, we often use substitution. So we solve x equals x of t in terms of t equals, substitute it into the other one equation. It does not work very well here to do that. So this is the trick that happens when we have sines and cosines, okay? So what we're going to do is we're going to take our equations that we have. I'm going to write them down on the screen first. So we have x equals 1 plus 2 cosine t. And I have y equals negative 2 plus 2 sine t. And I want to have the sines and the cosines by themselves. The coefficient in front of them is not a big deal, but I don't want the addition and subtraction over there with them. So I'm going to move the 1. So this is going to say x minus 1 equals, oh, did I leave it off? I did. This should say 2 cosine t. If you left yours off like me, please add it in. So this will now say 2 cosine t. And this one will say y plus 2 equals 2 sine t. If you really want to move those 2's over, you can. It creates a fraction which isn't very friendly looking, but it's not terrible. But they're okay where they are as well, so I'm going to leave them. Everybody good so far? Okay, so what are we going to do? Well, we're going to add them together, but we're not going to add them together as is. Like, I don't really want it to say x plus y. I'm going to have it say x squared plus y squared. So, yeah, and it's because I'm dealing with something that from the picture we know should end up being a circle, right? And at worst case, if it weren't a circle, then it'd be an ellipse, right? So we could have an ellipse going on here and the same sort of format would work. So what we're going to do is we're going to take the x minus 1 component and square it. And we're going to add it to the y plus 2 component and we're going to square it. And then the pieces that are equal to that, namely here and here, are going to go on the other side squared. So I'm going to have 2 cosine of t squared plus 2 sine of t squared. Now, some beautiful things are going to happen on the right-hand side. The left-hand side's actually in a great form. We don't really want to manipulate that at all. Do not go squaring that out. That will not help you. Okay, leave it. It's fabulous. However, the right-hand side needs some cleanup, and it's got some really nice cleanup that can happen. So if I multiply these out, I get 4 cosine squared of t plus 4 sine squared of t. And what do you notice? You can take the 4 out, and you have cosine squared plus sine squared, which is a trig identity. And what is cosine squared plus sine squared? It's 1. So all of this will reduce or simplify then into saying equals, well, 4 times 1, so 4. Yeah. So I have x minus 1 squared plus y plus 2 squared equals 4. Let's actually think about that compared to the graph that we drew before. I'm going to move the graph over here. Hang on. Okay, so here's my graph. So it's not plotted, but can you see where the center is going to be? Maybe on your paper better than on my screen. It's right here is my center. Is the center at 1, negative 2? It is. It's at 1, negative 2. And do I have a radius of 2? I do. So this matches from, some geometry course or algebra 2 course that you did somewhere way back when, what we actually found in the parametric world on the previous part of this problem. Okay? Do they all work like that? Well, no, because they don't all have sines and cosines in them. But this is sort of the way we deal with sines and cosines. The other ones deal with a little bit differently. So let's do another example. This one says to use a graphing calculator to sketch the curve defined by the parametric equation. So we aren't asked to eliminate any parameters on this one. We're just asked to use a calculator to work with this. So we're going to do that. We don't necessarily know, looking at this, what are going to be good values. Agreed? we're going to have to manipulate with it to see. So let's start by just entering this into our calculator. We have t cubed minus 2t.
And x1, y1, or?
Yes, as an x and a y, as x1 and y1, exactly. T cubed minus 2t and t squared minus 3. Now, if we all just graph it where we were before, we're going to get the same graph. It graphs really fast. Did it do it really fast for you? Yeah, it's like lightning speed. So right now the graph looks something like this. Whoa, wrong button. Fair? Okay, it should look something like that because we all have ours set up similarly. What's your window set up, Dylan?
Mine got rotated.
We got a negative somewhere.
Oh, is yours like this one? No, it's literally.
I think that's because you have a negative here instead of minus. So you press the buttons. Okay. Negatives and minuses, kind of the same thing. Did it work now?
Why does that matter?
Why does it matter? Yes, if yours is in a different window, but yeah. Okay, does everybody have a graph now that looks something like this on the graph? Okay. Any guesses as to what this might be if we graphed more of it? It might be an ellipse. It might be a sideways parabola, right? We did a conic section in 10.1. It's hard to know because right now our window isn't being very helpful, correct? And by the window, I don't really mean the x min, x max kind of things, although that might need to be manipulated as well. But I really need my t step and my t min and my t max to be different. In particular, my t min started at 0 in my last problem, right? Let's make our t min start at something negative and see what happens. And let's balance what's happening here. So I don't know what I'm going to be using. I'm going to try negative 2 to 2. T min, t max. My t step at 0.1, I'm going to go ahead and leave it for now. I might want to change it later, but I'm going to start with that. And then for my x min, x max, and everything, I'm just going to go with the negative 5 to 5. If you want to leave it in your square window, you could do that as well. So it had a funny x value, so that's okay. What happened?
It's above.
Whoa, it was not what we expected at all, was it? It isn't. It's a very interesting looking graph. Far more interesting than you get in function modes, right? It really is. It's a very interesting looking graph. So what gives? Well, we didn't have good information to start with, and we could change it too to see if there's anything else. But the reality is that it starts and stops on my screen, and it looks like it's going to continue in the same direction on each of those. But then again, it looked like that before, and it looked like it might have continued in a parabola form shape. So if you want to manipulate again, you certainly can. Make your min go from negative 5 to 5. You can make your t step a little bit smaller if you want, like 0.01. We'll try. We'll see if it'll work. I don't know. I'm going to make my window go from maybe negative 10 to 10 on the x min, x max, y min, y max, just to see if I can do that. You can also do a zoom out feature where it just zooms out automatically for you. That would be fine. Oh my goodness. Oh, it's okay. I was like, it's going to graph so slow. I'm going to be very frustrated, but it's not too bad. Okay. I think I've graphed enough to feel like this makes sense to me, and that it's going to keep going in both directions from here. What about you? Yeah? Okay. So let's sketch what we have. We need a little bit more accuracy than my zoomed out feature, so I'm going to zoom in this time now. So you can hit zoom, and you can do number 2. It'll zoom in for you if you would like to. It allows us to at least see some places where it's crossing the graph. Oh, that zooming in didn't work very well. I'll zoom back out again a little bit. My minimum on my y min is not helpful at the moment. So I'm going to make my y min go a little bit lower. Let's go negative 5. All right, so my graph looks like it's crossing over here at about 2. I'm pretty sure that's what it was, in fact. Is it 2? Can somebody tell me for sure? Can you tell? Yes, excellent. And then over here at positive 2. I do hit at a point that looks like it's at 1. Is that true?
Yeah.
Okay, it's crossing at 1. Where does it cross below that? Yeah, at negative 3. Make my graph go a little lower. Right here. So these are the points that I'm going to plot as sort of the precision points. And then the graph itself is doing something like this. That's not great. Let's try again. Now, normally in function notation, we put arrows on the ends of this, right? I mean, and it does go in both directions, but we also are using arrows to indicate direction of drawing, like how the graph drew for us. So let's reserve our arrows for doing that. Our arrows are actually moving on the graph from the left side to the right side, correct? On this one. They wouldn't have to do that, but we're going to put in some arrows that show direction for what we're doing. If you're concerned, and it's not a bad idea either, about is this graph going to look like the one that the book does or something like that, jot down for yourself what you used for your team in and your team max at the very least, right? That'll give you a good idea. Our team in and team max on this one, what I ended up doing was -5 to 5. It looked pretty close to this at -2 to 2, so that one was fine as well. But knowing this right here gives me some information that allows me, if I'm looking at it later, to be like, okay, that didn't look quite right. Why not? I can explain what I'm doing in terms of the t values that I chose. Okay, ready to try another one? Okay, these are a little bit different. These are not we're not being given an equation. So we're asked to find a parametric equation describing the given curve. It tells us that it's going to be a line segment. That's a very straight, well, it's straight. That's not what I meant to say, though. It's a very basic is what I meant to say. It's a very basic object, a line segment, right? It's a line segment that is supposed to be going from 0, 1 to 3, 4. We could graph this really easily, right? It's going from 0, 1 to 3, 4. This is the line segment I'm trying to parameterize, right? That's my goal, is to take that and to put it into parametric form. So I want to describe how we can do that in order to make that happen. So the first thing that we're going to describe is what x and y are doing individually in terms of the points. So x goes from what number to what number? 0 to 3. All good with that? We're going to do the same thing for y in a minute. X goes from 0 to 3. Now, you saw me do something. Isn't that right? Yeah. Preston, you good?
0, 1, wouldn't that be on the y-axis?
Oh, did I draw it wrong? I did. I'm sorry. You were correct. I don't have the graph in my notes. We'll go with that as my reason for making a mistake. How's that? Thank you. Thank you for helping us fix it. That's good. All right, better? Okay. X is going from 0 to 3. Now we're good with that? Excellent. X is going from 0 to 3. We saw something of this nature in a previous section. At the point when we did it, I was like, oh, look, there's parametrics again. I told you what we were going to do, but I didn't really justify why we were going to do it. Here's an example of what's happening here, and it'll sort of feel like something we've already done before. So we're going to let x equal AT plus B. It's going to be line. We're looking at a line segment anyway. That sort of makes sense. The x values are linearly going from one x value to another value. It is AT plus B. So we're going to let, or we can let, and it works nicely to do so, we can let t go from 0 to 1. So if we do that, then if, I'm zooming too much, then if if t is equal to 0, then x equals a times 0 plus b, correct? All good? But what do we want the x value to be when t is 0? We want it to be 0, right? We want it to be 0. Why? Well, because that's the first point we started at. The x value initially is 0. And if t is equal to 1, then x is going to equal a times 1 plus 0, because we just figured out that b is now 0, right? So what would A have to be for this? Oh, I'm sorry. What does X have to be in this case? What are we looking for X to equal at the end of the 0 to 1 value for T? Where do we want our point to end, or our line segment to end?
3.
At the X value of 3. We want this to be 3. So our goal is for this to be, let me do it this way. This 0 and this 3 are coming from the 0 and the 3 up here, okay? It's the X values that we want to have on the end points of our segment, 0 and 3. And we're trying to figure out what the B value and the A value are to make that happen. The first equation that we solved was really nice, and it told us then that B is equal to 0. The second equation then allows us to find that A is equal to what? 3, right? The A value is going to be equal to 3. I don't even need that there. So
basically, you want B to be the first initial X value, and then A would be the final.
not necessarily, but if we let the T values go from 0 to 1, then yes. Yes. That gives us an equation. So our parametric equation now then is that X is equal to 3T. At least the X value. We need to do the Y value still. And we're going to repeat this process. So let's get practice to try doing that in another form. So let me make that small. Erase those marks. So let's do the same thing for Y. So Y goes from what to what? 1 to 4. Okay, everybody good with that? Y goes from 1 to 4. And so we're going to do the same thing. Y is going to be equal to, let's just use the A and B again. We can definitely use a different letter. If you don't like those, use C and D or whatever you'd like, but I'm just going to use them again. Again, whatever you use for your T on the first one has to be the same on the T here. So again, T goes from 0 to 1. And we're going to evaluate this at 0 and at 1. So if I put in 0 for T, it's got to be what the Y value equals at the first ordered pair, which is the value of 1. And that tells us then that B is equal to 1, right? So now my equation is Y equals AX plus 1. But now I'm putting in not X. Oh, and I did it there. Only here. Yeah, let's just put it in now, 1. The T's value is 1. So if I put in T equals 1 on this one, I should be getting back the second Y value, which is 4. What is my A value going to be for this one? It's 3 again. That doesn't always happen. It just happened to happen here. And the reason that's happening is because of the way that my slope over there is already a slope of 1. So the A values on both of these equations are going to match. So my Y equation for my parameter here is going to be 3T plus 1. So I have X equals 3T, Y equals 3T plus 1, and I have to specify over what interval I let Y or T go. This is for 0 is less than T is less than 1. Now, there's nothing special about 0 and 1 except that they're nice to work with, right? I could let T go from like -5 to 5, and I would have just plugged -5 in at one spot, and I would have plugged 5 in at another spot, and I'd have a system of equations to solve. Not as nice of a system because zeros are very friendly to evaluate with, and ones are almost as friendly. So 0 and 1 are simply nice values, but if they told you to use some other values, you could still do this. Your equations are just going to be a little bit more tricky to solve, right? Like let's say instead of doing, I think this is worth our time, so we're going to do it. Let's say instead of telling it that we were going to go from T equals 0 to 1, like it gave us the parameter for T, and it told you that it wanted T to go from -1 to 3. Okay, I'm going to plug in -1. So the first one is going to was X. So let me do it for X. X is equal to A times -1 plus B, and it's still going to equal the first X value, which is 0, right? I just don't have a very nice equation, right? I can't directly tell you what A or B are. But I'm about to get a second one. I can do the same thing for X when the T value is 3. So I have A times 3 plus B, and this would have to equal the second B value, which was 3. So my second equation now is 3A plus B equals 3. What would Go ahead. That's what I was going to ask.
Equations.
Yeah, what would you have to do to solve these? You'd need to do a system of equations. Substitution, elimination, matrices if you so desire, right? There's options here, and you could solve for A and B. Are the A and the B going to be the same as the ones we found? No, they will not, because our parameters are different, all right? But they will be equally correct. Now, I'd like for us to try what we found down here in yellow, or orange rather, because it's completed, and see with our calculator that it did what we expected it to do. Like it should give us that yellow piece on the side. That's the segment that we were told that we were supposed to be finding. So take your x1 and put in 3t. Your x2 is 3t plus 1. Your window definitely needs to have the parameter for t in from 0 to 1. Feel free to leave it at a 0.01 and so forth. We need our graph to go at least up high enough to see everything, so I'm going to choose for my graph to go from -5 to 5 on x and on y. And I'm going to graph it. Does yours look like the yellow piece up there? Yeah. So can you always check that you did it right? Of course you could. You should, in fact. It would be unwise not to, because you have the capability to do so. So I would encourage you to check those. Okay, you ready to do one that's a little bit more interesting? It's not a segment anyway. This one is the portion of a parabola. So we're doing the same kind of a description. We're finding a parametric equation for the given curve, finding parametric equations for the given curve. The portion of the parabola is what we're working on. That's y equals 2 minus t squared from 2, -2 to 0, 2. Okay, so we could graph this in function notation. You probably know what this looks like more or less. This is the graph of an x. This is a parabola graph. It's flipped upside down and it's shifted up 2 units. So the basic graph itself looks like this. And we're at a height of 2, right? It actually tells us that it starts and stops at locations. It's starting at 2, -2. So 2, -2. Hang on. Did I do something wrong? No, I'm fine. Over here. It starts here, and it's going backwards. That's what I wanted to see. And it's going to stop at 0, 2. It actually stops at the top right there. So it's this piece of the graph, give or take. It's just that orange piece that we're getting. Kind of feels like it goes backwards because it's moving the opposite direction of how we usually read our graphs. That's okay. All right, everybody good? This is what we're expecting to get when we're done. So we're going to write some pieces down here. So again, these are options. They're not the exclusive ways to do it, but this is an option. So we could let t go from 0 to 2. Do you have a question, Adrian?
Yeah, just give us on the test. You want us to write out the whole sentences, that kind of stuff?
You need to at least let me know what you're using. I'm going to write more than you necessarily need to right now because I want it in your notes so that when you look back later, you know what we did.
Yeah.
That's why I'm doing it right now. So does it have to all be written later? No. But you need to tell me where your t is starting. But like you could literally write down 0 is less than t is less than 2, and that would do the same thing. So, all right. So if t goes from 0 to 2, then let's, I'm sorry, and, that's what I meant to do. And what does x do? You can actually see this one from the points given. What are my x coordinates doing? This is not a trick question. Where do the x coordinates start? 2, and it stops at 0, right? X coordinates, right here. Starts at 2, ends at 0. Nod your head if you see where I'm going with this now. Are we good? Okay, still looking at the ordered pairs just like we did for the line segment. Okay, it starts at 2, ends at 0. We can write the same thing for y. Y is going to start at -2 and end at 2. Okay, so we'll write that in a second. But let's actually figure out how we can create an equation that does this. I need for my x values to do the opposite of the t values. So how do we get opposite things to happen generally? What would that sort of seem like? There's going to be a negative involved, right? But if I simply let x equal -t, that doesn't quite do it. What would I have to adjust in order to make that work? I could write the equation down, but I think we can think through it.
It would be minus TA minus B.
Well, we're going to have a minus t. We're going to have a minus t, but there needs to be something we subtract t from. Like right now, if I put in t equals 0, I just get 0 for x, but I don't want to get 0 for x. What do I want to get for x? I want to get 2. So how about I put a 2 right here? Does that make sense? Now, if I put in t equals 0, I get 2. That's good. What if I put in t equal 2? I get 0, and that's the other point that I wanted. So it works very nicely. If you want to write it out more like we did on the last one, you certainly can. You can make it work more rigidly. The x values are going to behave much like they did on the last problem. The y values are a little bit different, okay? So we know that y is equal to 2 minus x squared. How do we know that? It's given. They told us that, right? This is like geometry where you write down the first statement is given. That's how I know. They told me. They told me this. But if y is equal to 2 minus x squared and x is 2 minus t, what can I do to figure out what y is? I can substitute it in, right? I can take this expression for x and I can replace it. So my y is equal to 2 minus t squared. We'll clean it up a little bit because we can. So this is 2 minus 4. I end up getting plus 4t and then minus t squared. This ends up giving me negative t squared plus 4t minus 2. Yes. So this parameter for x, this parameter for y, and what is my t parameter that I haven't written down yet? Yeah, 0 to 2.
Oh, because it's negative. Just so it's that. Come on.
Yeah, are you good?
Yeah.
So is this the only answer? Well, no, it's not. If you wanted t to go from 0 to 1 like we did on the previous problem, we could have done that. Wouldn't be wrong. But we needed to do something, and it was kind of nice because the x values spanned a number set of 2 for us to have the y or the t values span a number set of 2. We could have done something similar over here. We could have said, well, I don't want t to go from 0 to 1. The x values span from 0 to 3, so I'm just going to let my t values go from 0 to 3. You could do that. It wouldn't be wrong. Let's just check the calculator real quick, make sure that that looks like what we were expecting, and then we'll call it a day. So on x1, we're going to put in 2 minus t. On y1, we're going to put in negative t squared plus 4t minus 2. On my window, I want my t min to start at 0 to go up to 2. I have no idea what my graph needs to look like, so I'm going to leave it where it was. Well, I do. It's on the screen, but I think it'll be good, so we'll leave it like it is. And if we graph it, I believe, oh, it's over here, sorry now. I believe it looks like that orange piece. So we can confirm that we did it wrong. And if it graphs wrong at this point, what do you know? You made a mistake, and you need to go back and double check some things, right? That's what we know. Do you have a question real quick, Adam? No? Okay, I thought maybe. All right, we will call that it for the day and stop there.